Okay. Hello, everyone. I'm William Joe, and I'm currently a doctoral candidate at UT Austin. And today I'll be presenting a study we have done as exploration science interns at the Lunar and Planetary Institute this year, titled Evaluating Regolith Displaced by Rocket Plumes During Artemis Human Landing System Descent. The biggest concern with HLS, which would be the main landing vehicle for Artemis 3 and 4 missions, is that compared to Apollo, it will be more than 7 times taller and 10 times heavier. This could mean that the effect of plume impingement from an Artemis HLS landing could be much more hazardous than that of an Apollo lunar module landing. Possible implications of having a much larger lander descend on the surface would be instrument habitation or surface damage on a much larger scale, trigger mass wasting events, or even create problems of visibility or stability during landing. The manufacturers of HLS have thought about using thrusters at the very top in order to mitigate the effect of plume impingement rather than use the bottom thrusters for landing. However, numbers showing the effects of this placement of thruster position on HLS and how much it will reduce plume impingement have not yet been investigated thoroughly. So the main goals for this project are to, one, compare the scale of erosion and far field impacts on HLS upper thrusters and lower thruster configuration for the Apollo lunar module. Also, to identify the most suitable configuration of HLS that reduces contamination and energetic impacts. And what we have done is develop the Lunar Plume Impingement Solver, or LPIS, to compare plume impingement of Regolith particles for selected landers, which are shown over here. So we're going to use the Apollo Descent Lunar Module, as well as simulate an HLS with lower thrusters and an HLS with upper thrusters. And we're assuming for LPIS that multiple engines or sets of multiple engines are represented as one big engine. For LPIS as well, we use the erosion mass flux equation and the properties of the nozzle gas at the surface to solve for the excavation profile and the total displaced mass using the domain represented as concentric cylinders shown to the left. We assume a scaling factor of around 3 times 10 to the negative 5 to fit Apollo lunar module observations of impingement at the surface. We're also assuming particles, Apollo 16 particle size distribution to convert mass to particles, and we're rejecting these particles with speeds derived from the spherical drag ordinary differential equation. And we're also going to be launching these at 3 degrees and using planetary ballistics to record the distance of these landed particles in longitudinal area bins, also shown to the left here. We first plot the near field erosion evolution in the figure to the left, which shows excavation depth in centimeters in the y-axis and distance away from the plume center line or the plume or the lander location in meters, and track the altitude of the lander with time. We descend at -1 meters per second from a starting altitude of 31.5 meters, which comprises the nearly vertical portion of descent. And this is equivalent to 5 times the height of the lunar module. And we now descend the spacecraft and watch the evolution of the crater the Apollo lander creates. And we find that this maximum excavation depth is around 2 centimeters, and the amount of displacement of Regolith displaced will be around 2.7 tons, which is really, really close to the observed quantities recovered for Apollo, with the scaling factor defined at 3 times 10 to the negative 5. Also, we find that if we were to consider erosion region as a depth greater than 1 micron, this region shown here, created by Apollo lander, will reach a diameter of 72 meters. And for HLS, we also simulate the same thing. We simulate the excavation profiles for a 100-ton human landing system with upper thrusters in burnt orange and lower thrusters in dark green. And again, we plot the excavation depth as a function of distance from the plume center line. And this time we set the altitude to 250 meters to keep the same geometric similarity of 5 times the lander height of Apollo, and descend not at a constant rate, but decelerating from a fast speed to or -11 meters per second to a slower speed of -1 meters per second using constant thrust. We see that the profile evolution, we can see the profile evolution and show that the erosion depth is around 1/3 of a centimeter for the upper thrusters and around 6 centimeters for the lower thrusters. The mass displaced is around 70 tons for the upper thruster, and for the lower thruster, 100 tons are displaced. If we use our predefined definition of erosion region as the region where an excavated depth is greater than 1 micron, then this region now reaches around 500 meters in diameter for the upper thruster and 760 meters for the lower thrusters. If we now track the far field particles ejected by the lander descent and record the amount of particles landed, in microns, tens of microns, hundreds of microns, and millimeter-sized particles. We obtained the plot on the left, which shows impact count as a function of distance from the spacecraft. And we find that in a region less than 100 meters from the lander, we are expected that 10 billion particles per square meter will contaminate the surface. And on the opposite end of the moon, we're expecting 100 particles per meter squared to contaminate a region on the opposite end. On the right figure, we plot impact counts for particles that only have a kinetic energy much larger than 10 to the negative 7 joules, also as a function of distance from the lander. We find that one way of comparing instrument damage between Apollo and HLS will be using a prior example of an instrument damaged by plume impingement processes. And Surveyor 3 is a good example of this. Surveyor 3 was located around 150 meters from Apollo 12 and showed damage with a surface density of around 10 to the negative 6 particles per square meter, likely caused by the impact of 10 micron size regolith particles. We see that this threshold of particles impacting at energies greater than 10 negative 7s, we get this plot to the right. And if we place a point on this plot that matches the observations of Surveyor 3, we can show that using this threshold energy fits extremely well with the simulated model of regolith particle erosion from the Apollo landing. So for our HLS study, we use this threshold energy and show later that the range of damage grows much larger with a much heavier lander like HLS. Now, if we compare total impact counts for HLS for both upper and lower thrusters on the upper thrusters on the left and lower thrusters on the right, we see that the upper thruster configuration will limit particles to just 10 kilometers from the landing site, while the lower thruster configuration will reach opposite side of the moon and impact surface density of around 5,000 particles per meter squared. And from these plots, we see that the impact counts have increased by a factor of 10 to 100 times, and we should expect the upper surface at maximum, at maximum 1 micron layer, be from the HLS ejecta. Now, if we compare an energy threshold of 10 to the negative 7 joules found earlier, we find that the impact count with energies greater than 10 to the negative 7 for both upper and lower thruster configurations, and we place a line of 10 to the negative 6 particles per meter squared to match surface density particles on Surveyor 3, we find that we show that one will need to go further out to a half kilometer away for HLS with upper thrusters and 5 kilometers for HLS with lower thrusters to find the same level of damage found on Surveyor 3. Anything within these ranges will have a much larger pitting surface density damage than Surveyor 3 and a much higher energy. And it's expected that 100 meters from the spacecraft, HLS would create 10 times more pitting damage. So around 10 million particles instead of 1 million impacts per square meter. Now, if we visualize the effects of HLS plume impingement on maps, we find that even using the upper thrusters will still cover a region, an area much larger than the Artemis exploration zone. And if one were to land near the center, one will have to travel out beyond the maximum displacement distance done by the Apollo 17 lunar rover vehicle to find pristine soil. And certainly the Artemis 3 mission will only find soil covered by HLS. If we assume that Artemis 3 will use a similar size scoop used by the Apollo mission, it is expected that the contamination near the spacecraft lander will be around the order of 100 parts per million and 10 parts per million 1 kilometer out. At 10 kilometers out, it should be diluted, but the overall effect close to the spacecraft will be 10 times worse for HLS than that of Apollo. Finally, here's some visualization of ranges where instrument damage caused by HLS will be much worse than the one found on Surveyor 3 during Apollo. Work on this map can be refined further if instrument damage ratings, such as impact surface density and particle impact and density, maximum particle impact energy that a spacecraft instrument can withstand, are defined for future instruments or structures for bases. To conclude, we have these 4 takeaways. 1, HLS will be much worse in terms of regolith displacement than the Apollo lunar module during landing. Upper thruster development is preferred over lower thruster development, and the upper 1 micron of the surface should be contaminated within the Artemis exploration zone. Instruments should be placed further than half a kilometer or 5 kilometers out, depending on the thruster type, upper thruster or lower thruster, to avoid similar instrument damage found on Surveyor 3. With that said, thank you to my colleagues that I've worked with this summer, as well as Dr. David Kring for his support, and I acknowledge Doctors David Goldstein and Pamardi Prem for their assistance with this study. With that, thank you so much.